Okay, so let us start the exercises. So first of all, we have exercise 1. Show that the definition of equality in definition 337, that is this is the equality of functions. That definition is reflexive, symmetric and transitive. This is one thing. Also, verify the substitution property. And the substitution property is this: if f and f tilde are two functions from x into y. We sometimes write like this: if two functions or more than one function have the same domain and same range, then we don't write them separately. We write them together like this. It just means that both f and f tilde have domain x and range y. Okay, so two such functions are given, and two more functions are given, g and g tilde, from y into z. They have domain y and range z. These are functions such that f is equal to f tilde and g is equal to g tilde. Then g composition f is equal to g tilde composition f tilde. This is the first one. So let's see the solution. So we first recall in brief what this definition says, definition 337. It just says that if we have two functions, say alpha and beta, having the same domain A and same range B, then they are said to be equal if alpha x is equal to beta x for all x in the domain. That is this definition 337. If such a thing is true, then we say that the functions alpha and beta are equal, and we write like this to denote that fact. Now we have to show that this relation of equality between two functions, equality of two functions, is reflexive, symmetric and transitive. So you already know what these things mean. In terms of this definition, reflexivity just simply is this: alpha is equal to alpha for every function alpha. Symmetry means this: if alpha is equal to beta, then beta is equal to alpha. And transitivity is this: if alpha is equal to beta, and suppose we have another function gamma, and beta is equal to gamma, then alpha must be equal to gamma. So this is reflexivity, this is symmetry, this is transitivity. And you can see that if you apply the definition 337, this definition of equality of functions, then these three things are actually obvious. So we are not going to show them here in the solution. Instead, we will just mention that they are obvious. We will instead look at this part, the second part of the exercise. So we write reflexivity, symmetry, and transitivity are obvious. Now we look at this property. Here what is given to us? Four functions are given. F, F tilde, G and G tilde. And F and F tilde have domain X, range Y. G and G tilde have domain Y, range Z. So you can see that these compositions make sense separately. G composition F and G tilde composition F tilde, they make sense because the domain of G is equal to the range of F. Here also, again, the domain of G tilde is equal to the range of F tilde. So the compositions make sense. But additionally, we are also given that according to this definition, F and F tilde are actually equal. And like that, G and G tilde are equal. Then the compositions must also be equal. So, So first of all, when you want to show that two functions are equal, according to this definition, it's not enough to just calculate the values of the functions at at any point in the domain. You have to first of all make sure that the functions have the same domain and same range. So here we first look at the domain of G composition F. You see, F goes from X to Y and G goes from Y to Z. So as we have already discussed, the intermediate step will vanish and the domain will be the domain of this function and the range will be the range of this function. So we write like that. Note that both G composition F and this function have domain X and range Z or Z. Then we calculate the values of the functions at common point in the domain. Let X belonging to X be any point then Fx is equal to F tilde X. Why? Because it is given that these two functions are equal and both of them have domain X. So at any point in the domain, their values will be equal. Which or we can write in bracket since F is equal to F tilde. Which implies G of Fx is equal to G tilde of F tilde X. Now, how are we getting this? You see, Fx and F tilde X, although they are equal, but still they are two elements in Y. and on y g and g tilde are equal, so the g values at this common point will be equal. I mean g value and g tilde value, they will be equal. Hence, but this is what? This is the value of the function g composition f at x. Likewise, this is the value of this function at x. So we get, but we have proved this for any point in the domain x. So g composition f is equal to this. So this ends the solution of the first exercise. Then we see the second one. Let f from x into y and g from y into z be functions. Show that what do we have to show? If f and that injective and subjective. If f and g are both injective, then so is G composition F. Also, if F and G, similarly, same thing, show that if F and G are both surjective, then so is G composition F. Okay. So first we handle injectivity. First assume F and G are both injective. Okay, we have to prove that G composition F is injective. So we take any point for x belonging to any point in the domain of this function, which is nothing but the domain of f, for any point x, not just any point but a particular point, any point which satisfies this. Oh, I have to take 2 points actually, sorry, for x1, x2 belonging to x. For injectivity, I have to show that at 2 distinct points in the domain, the outputs are distinct. For x1 and x2, such that x1 is not equal to x2. That's what distinctness means. We have fx1 is not equal to fx2. Why? Because since f is injective. Okay, injectivity of f allows us to write this, but fx1 and fx2 are elements in y because f is mapping from x into y, and these two are not equal, and G is injective, so their G images or the outputs of G are, when these are inputs, they will also be different. Hence, G composition f x1, which is nothing but equal to G of f of x1, is not equal to G of f of x2, which is G composition f x2. This is where we have used the fact that G is injective. We can write it here. Since G is injective, so the distinct points fx1 and fx2 in the domain y of G will have distinct outputs under the function G, and these are the outputs. So you see what we have achieved. We have taken distinct points in the domain x of G composition f, and we have proved that the corresponding outputs G composition f of x1 and G composition f of x2, they are also distinct. So that's why G composition f is injective. Is injective. Okay, next we show that G composition f is surjective if both f and G are surjective. Next we assume these functions are surjective. Note that the first part of the solution is over. So when we are assuming that f and g are surjective, there is no question of injectivity. They may or may not be injective, we don't care. We only are assuming surjectivity. Okay. Now what do we need to show? We need to show that this function is surjective, and this is a function whose domain is x and whose range is z. So that means if I choose any point here, then that point has to be the output of some input under this function. That input I have to find. So I start by choosing a point in the range. Let this be any point. Okay. Since G is surjective, so G is a function from y into z, right? So since G is surjective, this will be the output of some input in y under the function G. So that means there exists some y in the step y such that gy is equal to z. This is coming from the surjectivity of G. Also, y belongs to y and F is surjective. F is also surjective according to our assumption. So that means if I consider this as output, because f is a function from x into y. So if I am considering this as output, this also must come as an output of some input in x under the function f. So there exists some x belonging to x such that y is equal to fx. Now we combine these two equations. We thus have z equal to gy. Now in place of y we can write fx. So this becomes g composition fx. So we have shown that this arbitrary element in z appears as the output of this function g composition f when the input is x. Such an input exists. This shows that this is surjective, and that's what we wanted to show. So here the solution ends. Okay, now we move to the third one. So this third one is about the empty function. If you recall, an empty function with range x is a function whose range is x but the domain is the empty set. When is the empty function? Actually we should not write the empty function. An empty function we should write anyway. When is the empty function injective? Surjective and bijective. Okay, by the way, before we solve this, let's have a look at one of the consequences of this exercise. What it says is that if two functions are both injective, then their composition is injective. And if they are both surjective, then their composition is surjective. That means if they are both bijective, then the composition will also be bijective, because a function is bijective when it's both injective and surjective. So keep that conclusion in mind. We have not mentioned that here explicitly, but it comes about as a consequence of this, that the composition of two bijective functions is bijective. And that just is a simple conclusion of this exercise. Now we solve this, the third one. Okay, so what this one asks, when is the empty function injective? Let x be any set and let this be the empty function. Okay. Recall that the empty function does not need a rule of assignment. We don't need to say how f assigns elements of the empty set to set elements in X, because there is no element in the empty set. But now we have to prove that this is injective. Okay. Suppose, note that here our X is any set. That means this empty function corresponds to the set X. Once the set X has been fixed, there is only one empty function. In fact, that has been mentioned also before. But when we have not decided upon X, then there may be many empty functions. So that's why I said we should not write the. In fact, let me change this. When is an empty function injective? In the actual text, it's written the, however, it should be an. Okay. We want to show that this is injective. That means any empty function is injective. Suppose f is not injective. I suppose the contrary. F is not injective. Then there exist distinct elements x1 and x2 in the empty set such that fx1 is not equal to then they will be equal to, fx1 will be equal to fx2. Not being injective means there should be at least 2 points in the domain whose outputs are the same. We should be able to find 2 such points, at least 2 points having the same output under the function in the domain. Then only the function is not injective. Okay, but now this is not possible. However, this is not possible because the empty set has no element. So our supposition is wrong. That is, F is injective. Thus, every empty function is injective. I need some ink. So irrespective of the choice of X, that range set, the empty function is always injective. Okay, now next we have to decide when the empty function is surjective. Okay. Next, let X be any non-empty set now we are assuming X to be not just any set but any non-empty set. anything other than this set. Then actually this is a result we proved. We in fact had a name also. We gave it a name. It's called single choice. I don't remember the lemma number or something like that, but we had the name single choice. Then, so let me write that. Let me refer to it using that by single choice. Then we have some element x in x. That is, we can choose at least one element from x. Let this be the here we can write the empty function because now x has been chosen, it is fixed. So let this be the empty function. Now there exists no, okay, let me instead of calling this x, let me call it y, because now x, capital X is the range of my function, and since we are usually denoting range elements by y, so I call it y, I denote it by y. Now there exists no x in the empty set such that fx is equal to y. Again the reason is same, because this has no element. And what is the conclusion? This element in the range of this function is not the output of any element in the domain. So the function is not surjective. Hence, f is not surjective. Okay, so that means if I have an empty function where the range is non-empty, then that empty function is not surjective. But what about the empty function where the range is empty? Okay. Next, consider the empty function. Let me call it by another name, G, whose domain and range are both the empty set. Actually, we are saying f and g. You may feel that there should be some symbol to denote the empty function, just like there is a symbol to denote the empty set. But the empty function does not arise as frequently as the empty set arises in mathematics. So that's why, maybe that's why the mathematicians did not bother to invent any symbol for it, any special symbol for it. Maybe that's the reason. So anyway, so here I am denoting it by some other name, G. This particular one has its range also equal to the empty set. Now consider the following statement. for every y belonging to the empty set, there exists some x belonging to the empty set where this empty set is considered to be the range and this empty set is considered to be the domain, although they are the same thing, but you think of them like this, such that y is equal to gx. The question is this statement true? That's what we have to decide. It looks quite confusing because we are saying for every element in a set which has no element, then there exists again an element in a set which has no element, such that something happens. But you have to keep in mind that in this type of situations, most often it's an implication, and the implication here is this. We can rewrite this statement like this: if y belongs to empty set, then x belongs to, or then there exists x belongs to the empty set such that y is equal to